Hi, everybody. All right. Let's see. A bunch of people here. Um, does anybody have any questions? I see. I saw from the sign-up sheets that we have some brave volunteers uh, for the presentations, including one of our first next week, but none for today. So I'll just cover the material that I suggested for today, and and then we'll see how I guess the first presentation will start in office hours. So everyone, of course, is welcome to attend office hours. But for a portion of the office hours this week, we're going to do the discussion is going to be led um, by the people presenting. So so this week, Tyler is going to lead a discussion of the first problem of one of the homework problems. I think it's problem number 1, and problem number 3. I think from the sign-up sheet, Samuel is going to lead the discussion on that during office hours on Thursday. Okay, so any questions about anything before we get started today? Okay, and have people been able to access the homework okay? And is it clear how to submit the homework on Canvas? I expect that you guys are probably submitting home PSETs on other for other classes there as well. Does this look confusing to anybody? I actually haven't done it yet. So try if anyone has any problems, of course, just get in touch with us and we can try to help. Us meaning me and the me and the TAs. Okay, so if there aren't any questions now, let's get started. And as always, feel free to interrupt anytime. Okay, so last time just a brief reminder of where we ended up.
I don't think you're sharing your screen.
I am definitely not sharing my screen. Sorry about that. Okay. There we go. So last time we stated a theorem. If f is a continuous function on the circle on the torus, and if f hat of n is equal to 0 for every n, so if the Fourier coefficients are all identically 0, then f is the 0 function. So this is the uniqueness theorem that we stated last time, and we'll prove now. Last time we stated this theorem, and we proved a corollary. A corollary of the theorem. So we assume the statement of the theorem is true, and we prove that if f is a continuous function on the unit circle, and if the sequence obtained by taking the Fourier coefficients of f and taking their absolute values and summing over all integers n, if this sum is finite, so if the sum given by the Fourier coefficients converges absolutely, then the partial sums of f, so the partial Fourier sums of f, converge uniformly to f. On the unit circle. Um, and this is essentially Weierstrass's test for uniform convergence, together with the fact that that the limits of the uniform limit of a sequence of continuous functions is continuous. And then plus the third ingredient is the uniqueness theorem that we stated but haven't proved yet. So let's go back and prove the theorem. And in fact, so this theorem, as we develop some more machinery, in a few classes, we'll give a much easier proof of the theorem, but only after we've developed something. So it's hard to say whether what's easy or what's not. So right now we'll give a direct hands-on proof that's a little technical, but it's hands-on, and we can start. We can we can do it now without having developed any machinery, basically. Okay, so we're gonna I guess the proof is going to argue by contradiction. So proof of the theorem. Okay, so we're gonna, the idea is to construct a family of trig polynomials, so trigonometric polynomials, Pn of theta. Maybe I'll call this little n, or I think I call this pk of theta in my notes. So that theta, d theta tends to infinity as k goes to infinity. So when we integrate over, when we integrate the function, so, and this is under the hypothesis, under assumption that that this is true, that the Fourier coefficients vanish for every n. Well, okay, let me explain why this would do it. Well, this is going to do it very dramatically, in fact, because I claim that if we could find one such trigonometric polynomial for which this integral is non-zero, then we would obtain a contradiction. Why? Because so note. So I'll call this star. Star yields a contradiction because since what does it mean for the Fourier coefficients to all vanish? Sorry, integral against any of the e to the I'm switching notation all over the place here. Since means this is all zero, these are the Fourier coefficients, right, up to a multiple of 2 pi. And then any trig polynomial is just a linear combination of of some complex coefficients times these e to the I and x's, right? It's just it's a polynomial in e to the I and x, right? So so this implies that for all trig polynomials, right? If all the Fourier coefficients are zero, then integrating f against any trig polynomial is also zero. So so if we are able to find trig polynomials for which the above is true, then we definitely have a contradiction, right? Because here we have not only this is a dramatic contradiction. So okay, So the goal is to kind of find a trig polynomial to obtain a contradiction for which an integral like this is non-zero, and we'll in fact obtain this like stronger conclusion. But how do we do this? Well, we're gonna first, what does it mean for f to, we're gonna assume f is not identically zero, and then without loss of generality, we can assume we just pick a point for which f doesn't vanish. You could always just translate functions around, so why not choose that point to be, for simplicity, just to be x equals 0. So assume without loss of generality that f of 0 is not 0, and let's say that this is equal to alpha, which is bigger than 0. So let's assume that f of 0 is alpha, some number alpha, which is a positive number. If it was a negative number, then we consider the function minus f. Right, so without loss of generality, assume f of 0 is equal to alpha. And then since f is continuous at, in particular at x equals 0, there exists a delta bigger than 0. So if a continuous function is not 0 at a single point, then it's also not 0 in a neighborhood around that point, right? In fact, we can choose delta small enough so that f is bigger than alpha over 2 in a delta neighborhood of 0. There exists delta bigger than 0 such that f of x is bigger than alpha over 2 for every x in minus delta. All right, so this is just a consequence. This is now just, we've just read off the consequences of assuming that f is a continuous function that doesn't identically vanish. And we can assume that f doesn't vanish like this. Here's a little picture. So here's f of 0. This is alpha, and then it's continuous nearby. So even if it starts decreasing, we can still find a delta and minus delta, so that f is bigger than alpha over 2 in this delta neighborhood. Okay, so now let's start building our trig polynomials. So let's let p of theta, I should stop using theta, I think I've been using x. Let p of x be defined by epsilon plus cosine of x. Okay, so what's epsilon? Where epsilon is a positive number chosen small enough. So what we've done is just taken the cosine, we're just taking the cosine function and then shifting it by epsilon. But we're choosing epsilon small enough so that p of theta is less than 1 minus epsilon over 2 if the absolute value of x is bigger than or equal to delta, and okay, we only have to go up to pi. All right, and then let me, so this is how, so we're now fixing another constant, epsilon. So first, we've chosen such a delta. Delta's fixed. Now we're picking any epsilon so that this is true, and I'll draw a picture in a second to show you why we can pick such an epsilon. It's, again, just because of the shape of the cosine function. And then now, this is a technical proof. We're going to choose yet another small parameter. So next, choose eta bigger than 0, a third small parameter with eta less than delta. And I'm going to try and draw a picture in a second to clarify all of this. Such that, well, p, what's the behavior of p at the point 0? So we're going to try and make our trig polynomials have a peak at x equals 0. So for this first one, I'm going to just try and make this function bigger than 1 at 0, strictly bigger than 1. or bounded away from one from above. So this is why I've shifted with this epsilon. So at 0, p of 0 is equal to epsilon. Is equal to 1 plus epsilon, right? Because cosine of 0 is equal to 1. So p of 0 is equal to 1 plus epsilon. So if I look at since cosine is continuous, I can choose a small enough neighborhood of 0 so that cosine 1, close enough so that this function stays above, say, 1 plus epsilon over 2 near 0. So this is how I'm going to choose eta. So this is just eta is now just using the continuity of cosine. Choose eta bigger than 0 with eta less than delta, such that p of I've been switching. I have theta in my notes, and I started using x on these slides. So I'm sorry if I'm going between theta and x. I'll try to fix the typos as I see them. So choosing eta such that p of x is bigger than 1 plus epsilon over 2 if x is less than eta. So here's the picture of p. Here's 1 plus epsilon, that's its value at 0. And then to the right, it looks like this. So here's, say, 1, and here's 1 plus epsilon over 2. So here is where I pick eta to be, so that the function stays above 1 plus epsilon over 2, and then eta neighborhood of 0. And then if here's 1 minus epsilon over 2 down here, and I choose delta. I choose delta so that this function stays below 1 minus epsilon over 2 if I'm between here and pi. And same for minus. The picture looks, cosine's even, right? So the picture looks the same to the left. And since I've shifted up, I also stay below 1 minus 1 plus epsilon over 2 down here. By the time I get to pi, because I've shifted up by epsilon. Okay, so this is p. And now what I'm going to do is, it's unclear what I get integrating f against this function p. It's not quite clear, but I'm going to try and make this function more dramatic. So I'm going to take p and I'm going to raise it to the kth power. So I'm going to define pk of x to be equal to p of x to the kth power, where k is a positive integer. And so what does this do? Well, this is just going to spike the function at 0, right? Because the function is what happens when I raise this to the kth power. If I look inside this eta neighborhood of the 0, the function's bigger than 1 here. So raising a number bigger than 1 to the kth power makes it bigger, right? I'll get a bigger and bigger number, and in fact, the peak at 0 will tend to infinity, right? 1 plus epsilon to the kth power tends to infinity as k tends to infinity. But then, since the function's smaller than 1 everywhere else, raising it to the kth power will shrink the function down to 0 outside of this delta neighborhood. So what ends up happening is that it's going to look, like this, as I let k go to infinity. So this is like, say this is p tan of x or something. Okay. So, but then, okay, each of these is a trig polynomial, right? Because it's just epsilon plus cosine of x to the kth power, and so I just get I'll just get in fact a polynomial in cosines, right? Which I can rewrite as if I like as a polynomial in e to the I n thetas, e to the I n x's. Um, okay, so um, okay, now let's get down to the business of estimating things. And I like this proof because this shows a bit about how um, we often do estimates in Fourier analysis, where we're going to estimate different regions of space differently with different techniques. So for f, now find a b. F is a continuous function on circle, so a continuous function on minus pi to pi, a compact interval, so it's bounded. So find b bigger than 0, such that f of x is less than or equal to b for every x between minus pi and pi. And let's now compute the integral of f against pk of x. So now compute okay, and what we're going to do is split this integral into 3 pieces. Each piece, the pieces, how we've divided the corresponding to our construction of p. So on the one hand, we're going to estimate, we're going to break the integral into 3 pieces. Okay, one when x is, let me go right. One piece where delta is bigger than or equal, absolute x is less than or equal to pi, plus the piece where x is between eta and delta, and then plus the piece where x is an absolute value less than or equal to eta. And I'll call these pieces 1 plus 2 plus 3 for shorthand. Okay, for piece 1, we're just going to bound this in absolute value. So I claim that piece 1 doesn't contribute much to the size of the right. So 1 plus 2 plus 3 gives the whole integral, and I claim that 1 doesn't contribute very much, right? Because if I just going to use my bound for p. So this is 1 is equal to this piece. So x bigger than delta between delta and pi. Pk of x. And here I know that, well, f is less than or equal to some constant b. So the whole interval is less than or equal to 2 pi. So I get 2 pi times b. And then for x bigger than or equal to delta and less than or equal to pi, I know that p is less than or equal to 1 minus epsilon over 2. So p to the k is less than or equal to 1 minus epsilon over 2 to the kth power. 2 pi b times 1 minus epsilon over 2 to the kth power. And this tends to 0 as k goes to infinity, right? Okay, so that piece is small, negligible. Piece 2, I can't say too much about. But I can say something important. So what can I say about the second piece? Well, in this region, I don't have a good lower bound for p, but I do know that that p is positive there. Or I guess maybe what I should, I guess I need to be careful. I should specify that here. So I choose delta like this, and right, and I this is okay, right? Because where's my drew my nice picture of cosine? I could just choose delta. I could just choose delta like this here, right? I'm choosing delta. I am in fact choosing delta where where p is positive to the left of delta, and same for minus delta. Okay, so I just forgot to specify that before. So for 2, I'm not going to put absolute values around it. I'm not sure why that. So the claim is that 2 is just equal to integral of eta less than or equal to x less than or equal to delta f of x pk of x is just positive, right? Because f is positive there, and in fact f is bigger than alpha over 2 when x is smaller than delta, absolute value less than delta, and p is positive there as well. So this contributes yields a positive contribution. And now for 3, I'm going to bound 3 from below. So finally 3 is equal to integral where I have good control over p. This is x less than or equal to eta f of x pk of x dx. Well, here I know that f is bigger than or equal to alpha over 2. I know that this interval is of size 2 eta, right? And I know that that pk of x on this interval is bounded below by 1 plus epsilon over 2 to the k, right? Because p is just p of x to the kth power. So this interval is bigger than, it's positive, and in fact bigger than this, which alpha and eta are constants that we fixed. So those might be very small numbers, but they're fixed and constant. And then I have, so alpha and eta are fixed small constants. But now I have something that tends to infinity as k goes to infinity, 1 plus epsilon over 2 to the k. So this tends to infinity as k goes to infinity. So for the whole integral, I have a sum of these 3. 1 contributes something that goes to 0. 2 contributes something positive. And 3 tends to infinity, is positive and tends to infinity. So the whole integral is positive and tends to infinity as k goes to infinity. So this all implies that f of x minus pi to pi pk of x dx goes to infinity as k goes to infinity. Which is, as we said before, so what we can do to finish our proof is we can just pick k, some k big enough so that this is clearly positive. This sum is 1 plus 2 plus 3 is clearly positive, and now we've contradicted the fact that f should vanish against when integrated against any trig polynomial. And so we're done. Okay, so that was a really technical argument, and I'm assuming hard to follow in real time as I wrote it down. But it's basically verbatim in the book. So please if it was confusing now, go over it. That said, also, are there any questions about it? Anything that didn't make sense about what we did?
Does this hold for complex functions f that are still continuous?
Sure. So good point.
Then the second integral number 2.
Let me exactly. So I should have said that. Thanks. Great question. And an omission by me at the beginning. Well, I started off talking about how f was positive at 0, etc. So implicitly, I was doing the proof for real valued functions. But you're right. We can easily extend this to complex valued functions as well, which we want to consider in the class. Maybe where's the beginning of the proof here? I'm going to add something to the beginning and say that, okay, if f is complex, note. So without loss of generality, f let's assume that f of x is a real function, because if f of x were complex, if f, right, f is u plus iv, So for any complex valued function, we can write it as its real and imaginary parts, where u is a real function and v is a real function. And if f didn't vanish everywhere, then either u or v doesn't vanish, right? At a point where f doesn't vanish, and then we could just apply this proof for real valued functions. Does that answer your question?
I think so. I'm going to think more about that to see why that last was true.
Yeah. So it's just that. Okay. So I think you've got the tools to think of it now. So it's just, if it were complex, either the real part or the imaginary part of the function, and we have just assumed per contradiction that f didn't vanish, either the real part or the imaginary part would have to not be zero, and then we go from there. Okay.
I have a quick question, if that's okay.
Yeah, of course.
So we started by assuming that f was continuous. We only use that it's continuous at 0.
Excellent point.
We shifted the non-zero point to 0. So wouldn't that mean that it only needs to be continuous like on the non-zero points or something like that?
Yeah. So I think so correct me if I'm wrong, but I think what you're observing is that we really only use the continuity of f at one single point, right, to prove the theorem. And you're right. We actually proved something stronger. We proved that if you have a function whose Fourier coefficients vanish everywhere, then f has to vanish at any point of continuity. So you're right. Well, we really only used that f was non-vanishing at a point at which f was continuous. And in fact, in your book, I think the stronger statement is stated. So I won't change it just to sometimes it's nice to make a theorem look as clean as possible in the statement, even if you prove something slightly stronger, or quite a bit stronger actually. But yeah, you're exactly right. All we used was continuity at a single point. Does that make sense?
Yes, it does. Thank you.
Great.
Another quick question.
Yeah.
How do we know that eta does not vanish as quick as the 1 plus epsilon over 2 to the power of k?
Sorry, can you just say that again? It broke off, I think, in the key point of your question.
When we choose eta so that f is greater than 1 plus epsilon over 2 to the power of k, how do we know that eta don't shrink so fast so that the integral actually diverge?
Okay, we're just going to, we're not, so remember we're just choosing eta for this single function p of x. So there's no k dependence. We can just choose eta at the very beginning like this and then stop. And it's fixed, right? So p of x is bigger than 1 plus epsilon over 2 here. So in particular, this implies that pk of x is greater than or equal to 1 plus epsilon over 2 to the k for every x less than or equal to eta, right? And for every k.
Yes.
Right. I think your worried is about eta changing when k was changing, right? Mm-hmm. But eta is fixed at the very beginning, and this holds uniformly in k.
Right.
Right. Because really the choice of eta was we chose eta just based on looking at the continuity of the cosine function. So we could fix it at this part of the proof, and then at some fixed number it doesn't shrink or anything like that. It's just we pick one small enough and then we stop. So that's the key point. So you're right to be worried about how the dependence of these parameters on various things in the proof, but I guess and we chose them one at a time. But then at some point before we started letting k move around, we fixed them all. We froze all those parameters. So that's the key point was, but you're right. That's the key point of the proof, kind of, is that we were able to choose these parameters independently of k.
Yeah. Thanks for that.
Any other questions? Okay. So, all right. So this uniqueness theorem is nice. I mean, on the one hand, we were able to then use some facts from our real analysis class to prove this corollary, right? Whose Fourier coefficients are absolutely summable. Then you have uniform convergence of the Fourier series. So then so the natural question then to ask is, can we find functions that satisfy this? And not just find some functions, but find big classes of functions that satisfy this. And a theme throughout the first weeks of the course, or throughout the whole course, and one of the things that makes this topic really fascinating is that decay. There's a deep relationship between smoothness and decay, and so meaning the smoothness of a function, how nice and smooth it is, as measured in how many derivatives are continuous, is directly related to how fast the Fourier coefficients decay. And vice versa, it turns out. So this relationship goes back and forth. That the decay of the Fourier coefficients is related to the smooth, tells you something about the smoothness of the function too. So we're going to start exploiting that relationship now. So the general the theme is that smoothness of f is related to decay of f hat n. So decay meaning how fast f hat n goes to zero. Okay, and the first manifestation of that. So a theorem. Proposition, I don't theorem, I guess, because if f is a C2 function, so maybe let me define some notation first before I, so recall some notation. CK of T is the space of all functions that are continuous on T. So maybe actually it's kind of cheap because I didn't define C0. All functions f from T to C, say, such that f is continuous and f k is continuous, or maybe fj. The jth derivative of f is continuous for all 1. So functions who have k continuous derivatives. So this is the space ck. And the theorem is that if f is C2, then f hat of n. So if f is twice continuously differentiable, so if f is continuous, f prime is continuous, and f double prime is continuous, then the Fourier coefficients are bounded by some constant times 1 over n squared. And the Fourier coefficients are decaying. In fact, we have a quantitative rate of decay for the Fourier coefficients. They're going to 0 faster than 1 over n squared for some uniform constancy. meaning maybe i.e. So what that means is C is independent of N. Okay, so and then some other notation. We can also write, instead of writing all that, so there exists some constant C for which f hat n is less than or equal to C times 1 over n squared. We're going to be proving lots of estimates like this. So it's nice to have shorthand notation for phrase. Can also write f hat n is big O of n to the minus 2 as n goes to infinity, where the big O notation is as follows. So big O notation. It's defined as follows. We say f equals big O of g if there exist is bounded from above by a constant times g of x. So it's just if one function is bounded by some constant times another function. There's also, maybe it's a good time to write before I prove the theorem. There's also, since there's big O notation, there's also little o notation. We say, so this involves more, it involves more than just a constant. So we say f, it's little o is about some asymptotic behavior. So we say that f of, say, x is equal to little o of g of x as x goes to p, say, if f divided by g goes to 0 as x goes to p. So big O notation isn't really about asymptotic behaviors, as if one function is bounded by some constant times another function. It's often used in that context. And little O notation involves some asymptotic behavior. So it's like if the ratio of two functions tend to 0 as you tend to a point, then we say the top function is little o of the bottom function. And this is a pretty common notation in like I'd say both analysis and number theory, like analytic number theory as well. Maybe more common, so more common in analytic number theory. But anyway, okay, so we'll be using this notation in class a lot because it takes a while to write whole phrases like this when I can rather just say f. I would rather just say f hat is little o of n to the minus 2. Okay, so let's prove this theorem. So if f, so we're going to try and exploit the smoothness of f to establish decay of the Fourier coefficients, and then once we've done that, then we can apply. So once we show the function decays like 1 over n squared, then we know it's absolutely summable as well, right? Because the sum from n equals 1 to infinity of 1 over n squared is finite. And in which case, all functions which are C2 have Fourier, their partial Fourier sums converge uniformly to f by the previous corollary. Okay, so let's prove the theorem.
Quick question.
Yeah.
Does this hold if you replace 2 by some other, say, k, in both places?
Excellent question. And the answer is yes. It's going to be the next thing I say after I finish proving the theorem.
Okay.
It will be clear once we, that will be clear once we once we do the proof.
Okay. We're doing big O here, not little o?
Big O. Yeah, this is big O.
Okay.
Okay, so you're kind of foreshadowing that little o might hold too. You're wondering if little o might hold too. In fact, it does, but we need a little bit. We need some. We're not ready to prove that yet.
Okay.
That's called the Riemann-Lebesgue lemma, which we'll get to later. Or it's similar to the Riemann-Lebesgue lemma. So we're going to prove big O, and this is already I think it's going to be a pretty easy proof. But it's already, I think, a really impressive theorem that it's like it's telling us something deep is happening, that smoothness somehow is related to decay. And we'll okay, so let's maybe before I just let me prove it real quick, and then maybe I'll make some more comments. So so this is the statement we're interested in is about n tending to or large n, right? Right, because we're interested in the summability of this. So let's zero. Let's just assume n's not zero. So n equals 0. It's okay. So or the statement for every say n bigger than equal to 1. Absolute n bigger than equal to 1. So say n is not 0. Then 2 pi times f hat of n, I'm just going to multiply by 2 pi on both sides to get rid of it on the left. On the right is the integral from minus pi to pi. Actually, I'm going to write 0 to 2 pi and then claim that that's okay too, so I don't get myself confused with my notes. F of theta e to the I n theta d theta. So this is the nth Fourier coefficient, e to the minus I n theta, sorry. And I wrote, this is unimportant for this computation, but I wrote 0 to 2 pi instead. I've been writing minus pi to pi, but since f is a periodic function, I can always just shift this integral. I can take the integral on any interval of length 2 pi on the real line, and I get the same thing. So this is the definition of the nth Fourier coefficient. And whenever presented with an integral, you integrate by parts just to see what happens. So let's integrate by parts. So this is equal to, let me set it up, integral from 0 to 2 pi minus 1 over I n d by d theta e to the minus I n theta times f of theta d theta. Right, I just rewrote the integral and noted that if I take that I can express this as this derivative. So this is in fact a deep fact in Fourier analysis. And then I can integrate by parts, right? And I get the boundary. I can evaluate the boundary terms. So this is minus 1 over I n e to the I n theta times f of theta evaluated at 0 and 2 pi. Plus, after integrating by parts, 0 to 2 pi, 1 over I n e to the minus I n theta f prime of theta d theta. So after integrating by parts, integrating by parts puts the derivative over on f, which I'm free to do because f is a C2 function, so it welcomes the derivative. All right, so I have this formula, and then I note that this integral, the boundary terms vanish. They cancel each other out because f is periodic with period 2 pi. So and so is e to the I n theta. So this sum here, when I evaluate at 2 pi and then subtract when I evaluate at 0, I get the same thing back again. So that's 0. So I'm just left with this second integral, and then I integrate by parts again. Right. I guess that the clue to the proof is I'm making some assumption about two derivatives of f, so I should try to involve two derivatives of f somehow, and then that tells me I should integrate by parts. And then I integrate by parts again, and just the same argument. I will get down again another I in. So I'll get 1 over I n times 1 over I n, which gives me 1 over n squared, because I times I is minus 1. And so I get minus 1 over n squared after doing this again. So I integrate by parts again. This is equal to interval 0 to pi f double prime of theta e to the minus I in theta d theta. So integrating by parts twice gives me that. And now I'm free to just brutally put absolute values in everywhere. So now 2 pi times f of f hat of n in absolute value is less than or equal to 1 over n squared times the integral from 0 to 2 pi. I'm going to put absolute values inside the integral, f double prime of theta d theta, because the absolute value of e to the minus I in theta. Remember, these are just the numbers on the unit circle. So this is equal to 1 for every n for every theta. And so this is, and then this is the c. This is the constant c in the proof. Is equal to c. C, as you see, doesn't depend on n anymore, which is important. It depends on f. The constant depends on f. So the decay rate that you get, there's a constant depending on f. But then the important thing is we get the 1 over n squared decay in n, which is what we were after. So that's the end of the proof. All right, and then to answer, I couldn't see on my screen answer the question. Was that Michael who asked a question about K?
Yeah.
So now you see there's a game that goes on, right? So this object is bounded by a constant. This is just by a constant because I know that f is twice continuously differentiable. So f double prime is a continuous function, so its integral is bounded. But there's nothing that stops me from integrating by parts more if the function was smoother, right? And as it's in one of the exercises in the book, that in fact, if f is k times differentiable, then I can integrate by parts k times, and each time I integrate by parts, I get down another copy of 1 over n. And so if f is k times differentiable, then the Fourier coefficients decay at least like 1 over n to the k. And so you see the smoother that f gets, the faster the Fourier coefficients decay. And so this gives our the first useful version of our theorem, which functions have convergent Fourier series. Well, the functions which are C2 or better have uniformly convergent Fourier series. Okay, so in this proof, though, we also so this means that so there's so corollary. This is corollary to the proof. F in CK T implies that f hat n is big O of n to the minus k. Okay. And then another corollary to the proof is that we have kind of an incredible formula here. And this is where Fourier series and Fourier analysis starts getting interesting with PDE, is that if I look at the, what do I have here, if I multiply through by 2 pi on each side, I see that I have f hat of n is equal to this integral against f prime, which is nothing other than the 1 over in times the Fourier coefficients of f prime, right? So, the corollary is as follows. So if I take a function, take its derivative, and then compute those Fourier coefficients. I don't know why I made this thing so this hat so big. If I look at f prime hat n, then this is equal to in times f hat of n. And it goes on. So f double prime hat of n is equal to in squared f hat of n, which is equal to minus n squared f hat of n. So finding the Fourier coefficients takes derivatives and turns them into multiplication by n, by in fact. And this is exciting for when you're presented with a PD, at least one that we can phrase for functions on the circle. Like PDEs are scary precisely because of the presence of derivatives. And well, here's an operation by taking a function and looking at its Fourier coefficients, which removes the derivatives, and that's anyway. This is Fourier analysis has been good to the subject of PDE because of this fact. Some people think too good, in fact, because we like you'll say PDE, we always just want to try to use some Fourier analysis techniques to solve, which can be a pain which is bad, I guess, when this doesn't quite work. All right. Okay, so we have these beautiful formulas, and this goes on. If I take the kth derivative and look at its Fourier coefficients, this is just given by in to the k times f hat of n. So these formulas then also give you the decay rates for the Fourier coefficients of functions which are k times differentiable. Okay. Okay, so corollary, did I state this? Yes, for k, this is for k bigger than or equal to 2. All right, so we're not gonna stop there though. In fact, remember Fourier was interested or conjectured that we have uniform convergence, or I'm not sure if you knew the word uniform convergence, but if we had convergence of the Fourier series for all continuous functions, and C2 is quite far away from saying just continuous functions can be much rougher than C2 functions, and we saw from applications that, for example, like plucking a guitar string, that the initial data might be rougher than a C2 function. So we want to go further. And let me just note that this type of analysis, it doesn't tell us anything about C1 functions, right? Because what we see from a C1 function, if we just know a function with C1, we could just integrate by parts once. We get decay of an absolute value of 1 over n, and that's it's not absolutely summable, right? So there's a reason why we started with 2 derivatives, because we wanted to get something that was absolutely summable. Okay, so let's go into more refined analysis. Of the partial sums S and F. And the idea is we're going to try and suss out some more structure. Okay, and the tool we'll develop first is the notion of convolution. So definition, given 2 functions f, g, that are so Riemann integrable, given two Riemann integrable functions. We set f on the circle, f convolved with g of x, f star g of x, is defined to be the integral from minus pi to pi, f of y, g of x minus y, dy. All right, so this is just a definition. And a couple observations. One is that just by change of variables, we have is equal to f convolved, g convolved with f. This is via change of variables. And then what's its significance for us? So significance, so I'm going to get to a couple properties of this convolution operation. And just note that this is an operation on functions. I take two functions in and it spits a function out, another function out, right? I have two functions on the circle, and then f convolved with g is another function of x in the circle, right? This is y gets integrated out, but this is a function of x. So significance for us. Well, let's look at the nth partial sum of partial Fourier sum of f. This is equal to the sum from n equals minus capital N to n of f hat n e to the I n x. So I'm going to expand out the definition of the Fourier coefficients. And then I have 1 over 2 pi minus pi to pi of f of y e to the minus I n y dy times e to the I n x. And as long as f is a nice enough function, I'm free to mess around a little bit. And here, so if f is an integrable function, then I'm free to put e to the I n x, which this doesn't depend on, this is a function of x. I can put this inside the integral. So this is n 1 over 2 pi times minus pi to pi f of y e to the I n x minus y dy, which is then equal to, I'm going to exchange integral and sum. This is a finite sum, right? For each capital N, this is a finite sum, so I can pull the integral outside the sum. This is given by 1 over 2 pi. Maybe in my definition of convolution, I want to include a 1 over 2 pi. Let's do that. Sorry, I'm going to add this 1 over 2 pi to the definition of convolution up here. Doesn't affect much. I should have done that at the beginning, I think. So this is 1 over 2 pi, integral from minus pi to pi of f of y times the sum from n equals minus n to n of e to the I n x minus y dy. Okay, and I'm going to write this as equal to f convolved with, I'm going to define this thing, and I'm going to call this dn of x. So this is a convolution, right? Here I have the function f integrated against a function evaluated at x minus y. So this is f convolved with the function dn, where dn of x is defined to be the sum from n equals minus n to n of e to the I n x. And this is called the Dirichlet kernel. So D is for Dirichlet. So this is the Dirichlet kernel. So the point is, when I nth partial sum of f can be written as a convolution of f with a function, with a sequence of functions, in fact, so dn of x. And the idea, idea we're from here is we're going to try and understand Sn of f by understanding this convolution. Okay. All right. So first, before we do this, I'm just going to state without proof of properties of convolution. Properties of convolution. I'm going to refer you back to your books for proof. So one, so let's assume that f, g, and h are Riemann integrable functions on the circle. So one is that it's associative, it's an associative product. Two, if I take f multiplied by a constant and convolve with g, this is equal to c times f times g, which is equal to f convolved with c times g. This is for every complex number c. Three, it's commutative product, so f convolved with g, I stated this already, g convolved with f. Four, what have I stated these all out of order. I'm sorry. I meant I had trouble reading my notes. So four is it's a linear product. So f convolved with g plus h is equal to f convolved with g plus f convolved with h. So this is linearity, these two. Then it's commutative associative, and then some more refined properties for us. So f convolved with g is continuous. Which is interesting, right? Because if I just took two Riemann integrable functions, they're not necessarily continuous, but when I convolve them together, I get a continuous function. So this means that convolution gains irregularity, right? So that's nice. So if I take two continuous functions, I convolve. So if I take two integrable functions, I convolve, I get a continuous function. And property 6, that it behaves very nicely with Fourier coefficients. So if I take two functions, convolve them together, and then compute the Fourier coefficients of the convolved functions, it's just equal to the product of the Fourier coefficients of the two functions. So this is a nice property. Gives you there's nice structure here. Okay, so I think I'm going to leave these. So the proof is an exercise, and see the Steinschik-Archie book. These are all proved there. 5 and 6 are really the only ones that take more than a line to do, but they're not so hard. So this is a good real analysis lemma. Um, any questions so far about the definition of convolution? Convolution of two functions? Okay. Yeah. So exercise C, the book. These are 5 and 6 are a little bit more involved. Yeah. Okay. All right. So the next notion I want to introduce is the notion of what's called approximate identity. So kernel, which is a limitation from Stein and Shikarchi's book. Sorry about that. Noise on my computer. Okay, so good kernels, and the more typical word are approximate identities. Okay, so definition. So one point I want to make. So this is so we have this convolution operator. We observe that the partial sums of partial Fourier sums of a function are given by convolving with a family of with a function, the Dirichlet kernel, and that there's a family of these the functions which we'll call the Dirichlet kernels. So I'm going to next prove a lemma about an abstract family of kernels. I'm going to classify kernels into good ones and bad ones, kind of. So the definition of a good kernel, and these are called approximate identities usually, is that a family of functions on T is called either an approximate identity, or say family. The book calls them family of good kernels. If 3 properties hold. If A, for every n, the integral 1 over 2 pi times minus pi to pi. So the integral of kn of x dx is equal to 1 for every n. So they're a normalized family. They're all each of these functions has mass 1. They're all integrate to 1. B, which is different than A, very different than A, that if I put absolute values inside the integral, the family is uniformly bounded. So there exists an m bigger than 0, such that for every n bigger than or equal to 1, integral from minus pi to pi of absolute kn of x dx is less than or equal to m. And note, importantly, that here I've put absolute values inside the integral. So these are uniformly bounded in this sense. And then C, for every delta bigger than 0, so there's some condition about what these look like outside of the origin. For every delta bigger than 0, integral from, if I look at all x bigger than or equal to delta, less or equal to pi, of absolute kn of x dx tends to 0 as n goes to infinity. Okay. So let's flesh out this definition. This is an abstract definition at this point. These are what's called a good family of kernels satisfies these 3 properties. And what are these? So in physics classes, people call this, or in physics, people call such things the Dirac delta function. in math, or rather, these approximate what's called the Dirac delta function, which is not a function; it's a distribution. It's a well understood object. It was a confusing object for a long period of time, but it should be thought of. I'll flesh this out a little bit more in a second. So what's going on here? These functions all integrate to 1. So they have some mass, but there's if I look away from the origin, none of that mass is left, right? The function, the integrals tend to 0 if I just look at the absolute value of the function away from the origin. So I should think of a sequence of functions where all the mass is being concentrated, or there's a unit amount of mass and all of it's being concentrated at a single point, kind of as I let n go to infinity at 0. So what these look like, so a picture of what a good kernel looks like, is something could be going on out here, but at the origin there's unit mass. I'm concentrating. These are terrible pictures, but an example. So it's easy to construct such families. Just take any function. Phi, take any positive function phi, such that integral integrates to 1. So let's take any positive function you like that has integral equal to 1, and then set kn of x is equal to n times phi of n times x. And you can check that such a family yields a good kernel, a good family of kernels, or is an approximate identity. Okay, so why did I bring up the delta function? This is kind of like okay. So one is this picture that I drew. This is an awful picture. Not much better. But what I'm trying to emphasize is that what happens, what these conditions imply is that as I let n get larger, it's kind of just a function which has all of its mass, a unit amount of mass concentrated at a single point at x equals 0. And the theorem about good kernels is that they and this is why they're called approximate identities. So if I let kn be an approximate identity, so a good family of kernels, then if f is integrable on t, the limit as n goes to infinity of f convolved with kn of x is equal to f of x whenever f is continuous at x. So if f is continuous on all of t, then f convolved with kn converges to f uniformly. So if I have a family of kernels and I convolve with a function, with a continuous function, then I recover the function back again as I let n go to infinity. And this is the Dirac delta function, delta distribution. In physics is an object such that F convolve with delta is equal to F. So it's the identity. It's the identity for convolution. So on the previous page, I started discussing how convolution has these nice properties. It has these algebraic properties. It's a type of product. It's commutative. It's associative. If I convolve with the zero function, then I get zero, obviously, right? So there's an additive identity. And then the delta function is supposed to be the multiplicative identity for convolution. The problem mathematically is that there's no such function, really. There's no such object that you can convolve and just get back the function back again. So there's in fact no you'd like this kind of multiplicative product, but it doesn't amongst functions. And in fact, a French mathematician, Laurent Schwartz, in the 60s, created a theory of distributions, and he made this rigorous. He kind of expanded the class of functions to say that functions sat inside this larger class of objects called distributions, which the delta distribution was a member of. So he made this all rigorous. This is kind of a common thing in physics for a long time. People wanted such an object, but mathematically, the way we can think about this delta function is that, okay, we can't find a function that does this, but what we can do is the next best thing. We can find a sequence of functions that doesn't, any single one of them doesn't yield back f again, isn't the identity for convolution, but as I let n go to infinity, I recover f again. So this is like saying that an approximate identity is the next best thing to having an identity for convolution, or a unit for convolution, a multiplicative identity. It does this in a nice sense in the limit, right? If I look at a continuous function and let n go to infinity, then this family of functions converges uniformly back to f again. So this is an object that we now, with our real analysis background, we can make nice sense of. Does that discussion does that make sense to people? I see some nodding heads. So
is a distribution on a torus just like a measure?
Yes, but we haven't. So we haven't gotten to measures yet. So we'll talk a little bit more about that. We're gonna discuss measures. We're going to discuss one measure, the Lebesgue measure, but yes, measures are relevant in the discussion of distributions. Yeah, but yes, in fact. Is that okay? There's so more general than functions. You can pass to things called measures, and we'll get to that. We'll get to that later in the course. But yeah, there's nothing scary really about the theory of distributions. It's just you end up with questions like this, gee, it would be nice to think of these k-ins. You look at this theorem that we proved, approximate identities, and it'd be nice if these k-ins converge to something. Or in what sense do the k-ins, what do they converge to? And you'd like to say, well, there's this object called the delta function or delta distribution, and k-ins, any approximate identity in the limit yields this delta function. It'd be nice if this was a convergent process. There's the k-ins by themselves in some sense. And then so it turns out that this doesn't work amongst the class of functions, and so you try to enlarge this in some way or generalize a notion of a function. And if you take probably, I think in 101, if not in 101, then it definitely, if you take the first graduate class in analysis at MIT, or a first graduate class in analysis, you'll study the theory of distributions. It's not that exciting at the end of the day. We won't spend much time on them in this class. We're going to try and get to some of the cool stuff. But it's a kind of an essential tool. It clarified a lot of things in the 60s, and modern analysis in PD would be sort of impossible without the theory of distributions. But but it's one of these things where you have to go through it once in graduate school, and it's a little bit painful. But then once you do, you feel a lot stronger, and then feel the need not to have to worry about it anymore. So it's one of those theories. Study it once, and then you're like, oh, I don't need to worry about this anymore, until you need to teach it, and then you get a new appreciation, et cetera, et cetera, et cetera. So, the life of a mathematical theory. Okay, so maybe we prove this theorem first. Oh, it's 4 o'clock. Oh my goodness. Sorry, I'm so sorry. Please, someone stop me before this happens in the future. We'll stop here, and we'll gather next time. I'm very sorry for going over time. Sorry about that. Talk.
Thank you.
Feel free to leave, and I'll stand for a second.
Thanks.
Thank you.
Thank you.
Thank you.
Yes. And I realize I have to run. I have to go to a seminar, so I have to run too. So I don't have time for questions at the moment. Bye, guys.